get started. I guess type of so my goal is to finish this, but if we don't, we'll do it next Monday. So it's not something that we have to finish, but hopefully we can finish this one. Because this class, this topic form the foundation of the rest of the semester. Okay. And the idea is that we try to look at what is the sample mean looks like, right? What is the mean of the sample mean? What is the variance sample mean? And what is the distribution of sample mean? And that's the main thing. Okay. So let me quickly review what we have done, right? So population is the thing we study, right? And sample is the thing we have data to study. And note that the data is not something we know which observation we get before we talk to, right? And the thing is like, it's not good to fix in advance. It's better to random sample, as we argue, right? Because if you know who we talk to, then you're already very biased, right? So we really want to have a random sample, because by random sample, the feature of random will allow us to say what's going on in the population, right? I always talk to one of you, and I want to think that is something that represents CHK, probably it's not, right? If I randomly pick up some people, then probably that would mimic the idea what's going on in the population, right? And that is the idea. And we have the simple random sample, which something nice in math, but in theory, but it's very difficult to achieve in practice. The idea is everyone is equal likely to pick up, and everyone pick is independent of the others. Okay. And because the feature of simple random sample then means that the same mean, same variance, and zero covariances. And the next is, again, is the most important part of this class, right? Is the definition of statistics, which is a function of sample. And we talk about sample is a random sample, which means that they are all random variable. That means that statistics is also a random variable, and it depends on what sample you are drawn. And in our example, we assume this is a sample mean and sample variance, right? And that the reason is different from topic one is that we are not talking about population, right? Population has no uncertainty. This is what we get, and this is what calculate, right? That's why we call population mean and population variance is the thing we want to study. We got all the data out of those, and we want to calculate mean and variance on uncertainty. That is how to describe the data, right? That's why we call descriptive statistics. But now this is not, because sample mean is not something we're interested in, but rather the sample mean is we use it to guess what's going on in the population mean. And sample variance, again, we will see is the way to guess the population variance. We'll talk about guessing, or what's called estimation, in the next class, or next week, next Monday or next Thursday, we'll talk about those. But at the moment, the reason we want to focus on this is because they are useful to guess what's going on and tell us a lot of information there. Okay, we're not interested by itself, by them. Themselves is not interesting, but they have uses which is very useful. Okay. And again, sample means adding up. As I said, this capital letter, right, are not random variable, right, compared to the small letter observations, right? So I think that is very useful. Here we do have I'm sorry for this. We have sample mean and sample variance, but we want to know the sample mean first, right? Sample variance, I don't have time to talk about, but sample variance, we have some other distribution. Okay, but we do know one thing we learned from last class is sample mean have very nice property. The mean of sample mean is turn out to be population mean, right? The variance of the sample mean is proportional to the population variance divided by sample size. Okay, which means that the larger the sample size you got, the sample mean will be more concentrated, right? You get more data, you get the larger sample size, you'll be more concentrated in center, right? So that would be the key point that you want to remember, right? This is saying that, right? If you do many sample, and then you have many sample mean, right? Then you would expect the average of these sample mean will be same as population mean, right? But what does that mean? It means that suppose, never do it, but suppose you have many lab, right? Do many experiment, and the average of this experiment we discover the main result we want, right? And this is saying that if you have a super large lab, super large lab, and that is right, then if you have different lab become larger and larger, then the variation between lab will be very small, right? Each lab will do their own sample mean, and these two are coming simply from idea of simple random sample, right? There's nothing interesting here. Not interesting, but there's nothing very deep here. The most deep thing is this one, okay? The P and the F looks like, okay? Law of large number said when n is large enough, P it just collapse to one point, right? P can be a lot of things, can be very different, can be very shape, right? Underlying. But the sample mean turn out to be when you have very large sample, the P will be just one point, or very close to that point. F is where collapse into one single point. Okay, and central limit theorem tell you that, okay, how you collapse there? You collapse to a bell. Okay, we collapse a bell. Okay, later we'll talk about one thing. Okay, and this is very important. Later, we here until here we didn't make any assumption. What is underlying population? Okay, and central limit theorem said the following, if you remember, is x bar minus mu, right, over the sigma square over root n is standard normal, right? So this is the exactly meaning of the central limit theorem. Okay, but you will see there's a one particular drawback for this is, as I also mentioned, is we have to know sigma. If you don't know sigma, then what can be done here, right? Or know the bell curve, but still I have to know sigma, right? I mean, of course, there's some way to estimate sigma, but for example, how do the sigma actually come from our idea that we call the empirical rule. Okay, you can, if the bell curve, right, most of the data are within 2 or 3 standard deviation, right? If you still remember the empirical rule, right? 68, 95, 99. Okay, and that's applied for bell. Indeed, there's another rule. That's more stronger rule. Is most of data should be within 4 SD, even though you are not bell. Okay, that's called Markov inequality. There's a Chebyshev inequality. Most of the data should be within 4 to 5 SD. Okay, so then how can you do that? You look at the data, you can calculate the range, right? The range you divide it by 10 will be the SD, right? Or 5, 10, or 8, depends on how likely you think the data is, but then you can estimate the SD in some way, okay? Even though you're not bell. But anyway, or you can use the sample variance to calculate the bell, right? But still, you don't know the exactly sigma, then this is not very useful, right? So we will talk about today is what we call the student T distribution, which we also hint last time. Is now we make some assumption, okay? Is if the population is a bell curve, then we can replace this guy by sample SD, but this is no longer normal, but with T distribution with n minus 1. So it's almost like the bell. Almost a bell one. If you basically is, if you're willing to assume the population is a bell, okay, I still don't know sigma as well, but I make bell, okay, then I can replace the sigma by our sample SD, okay? And I only need to replace the bell curve to almost bell curve, right? Remember, T is like the bell curve, but little bit fatter bell, okay? This I have that in the slide, don't worry. I just talk about what I'm going to talk today, okay? So this is something I'm going to talk today, but you can write it down if you like, but that is the idea of the T here, which we will talk about that, okay? And after that, before we talk about binary data, right? Binary data is either 0 or 1, and what we have before holds anyway, but binary data will make our case more simple. Why? Because remember, binary data, the mean, if you know the mean, you know the variance, right? We call that. You know the mean, you know the variance, right? Because if the mean times 1 minus the mean is the variance, right? Because if the population mean is like this, the population variance is mu times 1 minus mu, right? That is come from the binomial or binomial trial. So that means that we don't really require the student T. We just replace it by the sample proportion that we're done. Okay, then it's still normal. Okay, so don't worry, we'll talk about this. This is the goal of today. Okay, talk about T and also consider binary data. Okay, now let's continue ourselves to go slide by slide because I don't want to jump because you have enough time, so don't worry. We should be able to finish everything today. Now first, again, mean of sample mean is population mean. This is we know already, so I'm not going to repeat. Okay, that's the idea, right? If you many sample, each sample have a mean, and the average of this mean is population mean. And I have the example already. I think you should be able to see why this is true. I mean, there's a math behind, but I don't want to bother with that. Okay, and why it's good because it gives a confidence that on average we are hitting the target, right? Although we don't hit the target, but on average it's right. Okay, so we just, of course, some of people will think it's laughable, right? Because imagine, right, you are doing a basketball, right? Or you can football, maybe football, right? So you are here, right? Maybe you're going to hit the ball, right? Maybe you're Messi or Cristiano Ronaldo can hit somewhere here, right? It's very good, right? But if me, right, I'm the guy, which is me, okay? I'm not very good. Actually, I'm very bad at football. My son is better than I do. But if I hit here, I hit here, I hit here, what will happen? On average, I'm hitting the target, right? Average of this 3 point is actually inside, right? So unbiased actually mean this. Doesn't mean hit the target, but on average, the target still fine. Okay. But we'll talk about this next class about this, what called unbiasedness is very important. The second one is called this variance, right? So what does that mean? It means the following. Remember, actually, it's easy to see what variance is. Variance means the following. Again, I do an analog of football. Okay, and football is here. Okay, and football net is here. You're here. Okay, and if me, right, I'm not very good, right? So if I have a small sample, to a small sample, it may be here. Okay, the outcome can be here. Okay, if I have bigger sample, I'm much closer. The variance is more inside. So you just when any increase, it's just go in. Strength, right? It's still not there, but it's strength inside. Okay, so that's why the variance is proportional to the original data, original population variation, and also inversely proportional to the sample size. Right? The more sample you got, right, more data you have, then you are getting more accurate. Okay. So let me define standard error, right? Probably you remember. Standard error simply means standard deviation of statistics. So the error here means standard deviation of. Okay, the same thing. So the English is sample error of the mean is sample standard deviation of the sample. Okay, I don't know why they call it, but this is the terminology here. Okay, now we know already the example, so I'm not going to repeat. Okay, so as n goes to infinity, this variance goes to 0. So exactly what this is what the law of large number mean. Okay. If you want to write it loosely, it's very loose, like this. Okay. When the limiting case is the probability that you're different from anything from the mu is 0, that opposed to 1. So I don't want to bother you with this notation. And we said when sample mean is, we have a lot of sample, okay? Sample size larger, then we have, that's why I said there's a bell curve. Okay. And then we stop. Last time, I think part of that is this example, right? It's like the sample mean, right? The population mean is 5 and variance 64. Now we don't remember, we don't have anything to say about this shape, right? This original one can be mu is 5 here, right? Variance is 64, right? So it doesn't say anything about the bell curve. Okay? But what we said is if the sample mean, right? With 100 sample size, okay, what it looks like. Central limit of failure, even though the shape doesn't really look like what it's supposed to be, okay, it's still a bell curve at 5. Okay. And the variance is coming from this over n. Okay. It's when you increase the n, it shrinks a little bit more, right? When n goes to infinity, basically it's just 5. Okay. And the question is being asked is, okay, what is the probability at less than 4? Right? What's this area? Okay. And you look at this, right? Sigma is 64. Sigma square is 64. N is 100. Okay. And this is sigma. This is the sigma square x bar, right? Then you look at standard error is 8/10, which is 0.8. Okay. 0.8 means what? This is 1.245 SD. Right? That means that if you write the bell curve, this is Z, this is 0, negative 1.25, right? So this area is this number. How can you do that? If you want to look at the Excel, we just norm as this, negative 1.25, true. Okay, so this gives you 0.1057, right? Of course, you can do the table. I look at the Z table, look at where is negative 1.25, then you're done as well. Okay, so I hope that's clear. We've done that already. So now, is that okay? Is there any question? Okay, just a review still. Now we get to the binary data. So binary data is nothing but everything is just from 0 to 1, right? So ask whether you like spicy food, yes or no, right? And in that case, the mean is just proportion, right? Because if you don't like, it's 0. You like, it's 1, right? You add up all the data divided by n is the proportion of people who like it. Is that clear? Suppose you have 10 person, 5 say yes, 5 say no. Then how is the mean? Mean is adding 5 0 and 5 1 divided by 10, which is 1/2. It's 50%. Right? You can imagine this. You can change different number actually with the same as proportion. Okay, that's the pi. And the variance turn out to be, you calculate, it must be pi minus pi. So you can try it, you can check it. It's not something difficult to see because this is a math problem. Okay, because everyone is 1 minus pi and 0 minus pi, and then you end up with this answer there. Okay. And this is actually, if you draw one sample, it is a Bernoulli because you draw one guy there, it's just whether it's success or not. And whether it's success or not is the same as the pi, right? Because proportion of people like it, right? Then the sample mean, right? Because this is you draw one, right? Then that is actually pi and 1 minus pi. Okay, if you draw once. but you draw many of them, right? And average of them, okay? And average of them, we can define sample proportion, which is number of people will say yes in your data, right? Because the mean is like this, right? Mean is whether yes or no is the proportion. And that is nothing new there. Just you replace the proportion by the sample mean at the pi, right? And the key is here, right? The key is here. It's this one, right? Because the key is this guy. The variance is pi times 1 minus pi. So once you know the pi, you know the mean, you know the variance. Okay? So I don't need to guess one thing. So in the proportion data, I just need to guess one. I know the mean, I know the variance, which is doesn't true for other thing. And the standard error just square root. Okay. So that means that if I can have this particular form, okay, here, this is the central limit theorem, like this. Okay, this is the formula. And you ask when this is a good, right? Because this actually is a binomial, but and when n pi and n times 1 pi n is 5, it's a good approximation. And usually shouldn't be a problem. Okay, because pi cannot be too small and too big anyway. But it will always true for our application, don't worry. Okay, but for your own assignment, your own application in the future, this may be able to take care about. But for us, it's not a problem. Our class exercise or everything should satisfy all this. Okay. So one thing want to mention a little bit is since later you will see this is more like binomial. Okay. And that's why normal sometimes can be used as a approximation of binomial. Okay. When I say X follow a binomial distribution, right, with N and P, right, and we can actually replace saying there's a bell curve. When N, P bigger than 5 and N times 1 minus bigger than 5, you can actually use this. Okay. This is called normal approximation of binomial distribution. Okay. But I'm not going to go to that because we said everything. I mean, you may ask what is different from the central limit theorem. Central limit theorem is saying the sample mean following normal. Here is say, give me any binomial distribution, need not be sample mean, anything. As long as you give binomial, I say the normal is a good approximation to that. So that is the idea. But it's technical, so I don't think if you don't want to care about that, you don't have to. So the example would be like, I have a special N and P, and I want to calculate that, right? Of course, you can actually do the Excel can do it, right? In old day you can't, but now with Excel, so we can actually we need this approximation because you can actually calculate that directly. But in the old days, you don't have the calculator, so that's why people can use this approximation. Say, okay, although I know it's binomial, but we can change it to normal, then do the calculation, look at the C table, okay? But now you can do it, right? Because this, if you actually look at the Excel, right, this is just binom this, right? 55. That's the answer. Okay. But this should give you something similar to this one. Okay. But I'm not going to go into the detail of the approximation there because it's also. So here I want to talk about the T distribution. That's most important because although we say we use central limit theorem, right? But we don't use directly. Why? We have to add one more step because we have no idea of sigma squared. Right? If we know, then we're done. Okay. But the problem is, no, I'm so sorry, we don't know. Okay, we don't know this guy. It's a problem. Okay. Or if we know, nice. Or we have some idea, that's okay. But very often we don't. Okay. In some cases, we, as I told you, we have some idea how to do it. If you have you know what the data is, you know what's the maximum, what's the minimum, you can have good guess about sigma square. But usually, we have no idea about sigma square. So what to go and do, right? If you don't have idea, is you use the sample variance. Okay. Do you note that this is different from the chapter 1? Chapter 1, this is not random variable. These are all random variable. Remember, this is sample. The sample mean is also random variable. Random variable, random variable. Okay. And as subtract is also random variable. So this sample means random. Sample variance is a random variable. And you calculate the square root, become this guy. Okay. Okay. Remember, this is the sample variance, right? And you use this to estimate the population variance. Okay. So the standard error, estimates as an error, is just replaced by this. Okay. This is to estimate the sigma square. Okay. And once we have this, then the problem is, okay, now we have, instead of sigma square with S, right? So what does it look like? Okay. And turn out that in general, we don't know. Okay. We have no idea what it looks like. If the original is like this, okay, if you replace it by this x, right, and if x bar minus mu minus sigma over root n, right, we know it's a bell curve, right? This is something we know already. Okay, this is what we call central limit theorem, right? The mu is here, the sigma square is here, right? This is 0, sorry. Right, this is 1, the variance is 1, right? But if we're asking ourselves is, what is this guy? Okay, unfortunately, it's not Bell. Okay, it's not Bell. I have no idea. I mean, in general, that we have no idea what's going on. Okay, unless we know the shape, we can't tell you what is this guy. This guy is not known. Okay, there's no way to know without knowing what's look like in the background. Okay, so we have to, in order to proceed, we have, at the moment, we assume the underlying also a bell curve. Okay, and some of you may ask, hey, what if not bell? Then are we done? Are we doomed? More or less, yes. We're doomed. We do not know. But is there any way to avoid this? Yes, we do. Yes, recall, some of you may have heard the name called Monte Carlo simulation or bootstrap method. There are many ways to do it based on the data. Okay, how to do that is we will try to look at the shape of the data. Look at the data we got. Try to guess what the shape may look like, original one, and we pretend we do some simulation idea to do it. That is what the modern method is doing. But I will not talk about in this class. It's way too advanced for our class. But there are ways to do it without assuming the underlying thing is normal. Okay, but our class make it easy. We focus on the case. We make this assumption. Okay, we will make this assumption throughout our course. Okay, the underlying is normal. From now on, we will make the assumption. Okay, so far the central limit theorem doesn't require normal. Okay, make sure that it's going to. Otherwise, if normal, the average must be normal, right? That's because remember the normal thing is you add, subtract, right? It's still normal, right? But we are now assuming that it's a normal thing. Okay, is that clear? So from now on, from this class, we assume our data coming from a distribution of normal. Okay, but before that we didn't make assumption, right? So from now on we make a normal. Okay, and I would argue that normal is what we need for this course. But of course, if you want to realize that, it's not our class. Okay, you'll be beyond. Okay, I don't think any undergraduate class would cover that, but maybe very advanced 4,000 classes. but usually just handle in the master level. Okay, if you really care. But I don't think we would to worry about this part. So that's why that means that it's okay. And as I said, in most of the case, because central limit theorem actually tell us that everything you observe is very likely to be normal anyway. So it's unless you're a very special case, otherwise normal is not a too big assumption to have. Okay. So that we said is called normality assumption. We will make the assumption that the underlying population is normal. Okay. So what does that mean? It means that we don't need to use central limit theorem to get the normal, right? Because if this is the bell curve, okay, whatever how many days, no matter even just one sample size or 2 or 3, this is still a normal, right? Right? Because what is this guy? This guy is x1 plus x2, xn the other n, right? And each one is bell curve. Remember, adding bell curve is still bell curve. And divided by n is just divided by a constant, is the bell curve, right? So it's still a mu sigma square of right? So here, I don't need any central limit theorem. Fair, right? This is something we don't need central limit theorem. So that means that n can be very small, have no problem. Okay. And the next thing here is to say, this is what we call the normality assumption. Okay. The next thing here we would try to say is, okay, as I said, under normality, this is what we have, right? We say sample mean will follow bell curve. Because under is bell curve, the sample is bell curve. Of course, the variance is smaller, as we know, right? Because you pick the bell curve up, right? And you average them out, it's more likely to shrink, right? The idea is very simple. You can imagine, like here, right? You get some data from here, right? It's more likely to be near the center, right? The data is more likely to be here than outside. So it's more concentrated in the center. So the variance must shrink, right? It cannot be the same variance, it must shrink. And the next thing is, okay, because of that, we will have this result, which essentially said when replaced by the sample variance instead of sigma, right? This is what we call T distribution. Okay. And T is invented by 1930s by a mathematician called, I think, Morset. And he used the pen name student, right? That's why I got student T. Okay. And turn out that this will depends on number of sample, right? If remember, T infinity is exactly normal CO1. Okay, which is not surprising, right? If you keep getting data, then you should get back to normal there, right? But if not, then you will be much thinner, right? Because remember, if this is normal, this is Z or T infinity, right? What is T1? T1 something like this, right? Sorry, T1 something like this. T1, right? And it goes on because you're flatter on the both side, right? Then must be shorter at the middle, right? Because is more flatter, right? Higher kurtosis. Okay, it's all 0, right? Remember, it's all 0. Yeah. So that's it. Okay, it's not something too terribly difficult. So what do we want? Okay, after this break, okay, what do we have? Now it's a more realistic situation. Okay, we know the population follow normal distribution with mean 5. Okay, maybe this IQ is mean 100, right? We do not know the sigma square. Sigma square is unknown. We don't know. Okay, maybe it should be equal to a question mark, right? We don't know what's it. Okay, we have no idea how the shape, but we know it's a bell curve. Okay, and it's 100 here. Sigma squared? Question mark. Okay, it's X. Okay, we want to ask the question is, if we try to collect data from here, calculate the sample mean. Okay, how likely that? Sorry, it's not 5, right? It's not. It's the sample mean is 5. How likely that is less than 4.5? Okay, because the bell curve, this is also a bell curve. It's also the same mean, which is 5 here as well. Okay, and sample size 100, sample variance 8, so S squared is 8, is N is 100. Okay, the question is, how likely is less than 4.5? And you may ask why you why you want to care about that. It will be more clear next week. Okay, we'll do this calculation a lot, but the question is like this: since the bell curve, we want to calculate this area. Okay, how likely is it less than 4.5? Okay, remember it's the bell curve, right? But if we know the sigma, then we're done, right? Because this is the shape must be sigma squared over n, right? But we don't have sigma, so we can't use this result, the bell. Okay. But luckily, if we know this is the bell, original bell, then we know this is going to be a t distribution. With degree of freedom 99, y 100 minus 1. There will be something like the bell as well, right? And how can you do that? Still, this is mean 0. And what's different between this? Right? It's 0.5 over SD is this over 10, 100 and square root. Okay, will be 8 over 100 square root. Okay, so this is how the difference is where this location, which is negative 1.768, which is here, right? So the question is, in this area, the same as this area. Okay, so, and then of course, how can you calculate this guy? This is area on the left hand side, so just t dot this negative 1.768. Remember, you have 99 here, just put in 99 and then true, then give you the answer. Okay, so that would be the idea, because the t distribution, you tell them the number there, you tell them look at 99, true because on left hand side, right? If you do right hand side 1 minus from that, then you're done. We will be doing this type of calculation a lot for the rest of semester. Unfortunately, this is something that the t you will do a lot. Normal, you do it, but not that much. But t is the thing that you do often. Okay, as an exercise, maybe we ask the following question. What is the probability that the sample mean, same question, lot less than 4.5? Maybe you can try it for we'll talk about this after the break. Is say, this is more than 6, say. Okay, you can try it for when you have nothing to do, for your break, you can try this. Okay, we ask the question, what's the probability that X bar is more than 6? Okay, let's try this. And I write down here in case. We'll do this after break. Probability that X bar is more than 6. Okay, and we know that mu is 5 and is 100, and S squared is 8. Okay, so I want to know the answer to it. Okay, and of course I know the underlying is a normal, it's a bell curve, right? So this is a question. We'll talk about this answer after break. Okay? So try to do this. If you know how to do it, then you know very well. Right? Do remind you that this type of calculation we will keep doing again, again, and again. Okay, we'll do this for our estimation class. We'll do this for hypothesis testing class. We'll do this for ANOVA. Not ANOVA, but at least with the regression. Okay? ANOVA probably we will not use that, but at least the rest of the weeks we'll be doing this all the time. Okay? Is there any question? At the moment, you can try to do this. Okay? And we will talk about this after the break. Okay? Is that okay? Any question? If no, then we'll break. 15 minutes as usual. So enjoy the break. So let's see how we are doing. Can you upload? Well, it's very similar. So you can just ask. Every year I upload the last year paper. So if you want, we can just ask previous cohort because you will see very similar. So I don't think you benefit from doing more. You just make you more nervous because the same. I mean, you can just ask. I mean, it's not something I don't want because I guess it's you gain very little from that. And it make you work a little bit more. But you can just ask other people. I think it's not something not uncommon to see. Very sleepy. That's true. Yeah. Yeah, overall is fine. The weather is okay. Key point T. Assume it is a bell, then it would be T. So that is the main thing, right? Because we don't know. The problem is we don't know sigma. We don't know the population variance or population SD. So that's why we need to have this. Yes, that is the idea, right? So we assume because we don't know. So we assume the population is the bell curve. And that means that I can use the sample variance to or sample standard deviation to replace sigma. And then we know this is T. So that is the main thing, right? Let me repeat. The idea is we don't know sigma square. Okay, so that's why we can't use central limit from directly. So we have to replace this sigma by S, which is sample variance. But once we replace that, it's no longer normal. You become a T distribution. Okay. And the speed is okay, I guess. The overall, you can follow. Okay, so today I'm very little bit better because at least I have one people who is very good. Okay, maybe I guess it's outlier, maybe a mistake. Maybe he thinks it's very tired is one. So, but to this morning I taught the PhD class. So let's guess what do you expect? What do you expect? What would be the PhD class looks like? What do you think? Is something like this bell curve, or you think it's something like even this? Okay, so or you think something like this? So this is 1, this is 2, this is 3. Okay, who think it's 1? Who think it's 2? Who think it's 3? Oh, you guys are completely wrong. They're 1. They're not tired at all. I mean, they're pretty happy. Well, but understandable because they only actually take fewer courses than you do. I mean, PhD students only take 2 to 3 classes per semester. Of course, each class is more demanding, but they are not as tight as you do. Because I think you guys are pretty much because they live in the campus, many of them. So I think surprisingly, I mean, you guys are more crazier than them. Okay, I want to rest. Hopefully not in peace, but I mean, you are very busy, so hopefully. Do you know the bike is same as me? Is too tired. Oh yeah, that's true. I think everyone's very too tired, and I actually very tired because I when I get to the school, probably many of you know I'm taking the subway, and actually I sleep on the subway. I mean, I sit there and then just fall asleep 3 times. But luckily I drank 2 coffee this morning, so I'm okay at the moment. So now get back to the business as I asked you to calculate this. Okay, let me just do it again in the whiteboard. Okay, the question is just right here, right? Is I have a bell curve underlying the population. I know which is mu is 5. Okay? And I don't know this sigma square. This is something I don't know, so that's a problem. And because it's a bell curve, the sample mean is also bell. Okay. with mean also 5. Okay. This is sigma square for n, right? The problem is I don't know sigma square, then I have no idea sigma for n. Okay. But from the data, we know that s squared is 8. Okay. Okay. So I want to know the probability that is more than 6. So this guy, right? More than 6. Also, I want this area. Okay. How can we do that? And of course, I know sigma, then I'm done, right? Because it's just normal. I can do the calculation quickly. But if we don't, then what we do is consider T 99. Okay. 99 because n minus 1. Okay. And this 5 becomes 0 here. Okay. And then this is a T99 there. Okay. And what is the 6 here? It was this guy. How to convert it? This is the 6 minus 5, right? Because distance, right? And how to do that is square root 8 over 100. Okay. So it's some, okay? Then you calculate this number. Okay. And what's this number? Okay. Let's look at the Excel. Is 1 over square root of 8 over 100. 3.5. 3.5. Okay. 3.53. This number. So want to know this number. Okay. And this is the, if you do this, this is basically 1 minus T this 3.53, 99, true. Okay, so let me do it. Let me do it here. Okay. What I want is T dot this, or I 1 minus T dot this. Okay. And it's 3.53, 55. Okay. And then degree of 99, n minus 1, it's true. So it's almost impossible, right? It's not possible to have that, right? So it's too far away from that. So that's the answer. So the answer is 0. The probability, the question, just go back to the question, right? The question is, what is the probability that X bar is more than 6? 0. Okay, of course, you can write 0.0005. Right? If you really want, you can just write the 0.0031, right? If you want. But I guess it's okay to put 0 anyway. Okay? Yes. Okay, the question is how can you do it with T table? The T table cannot tell you this. The T table give you the what is 95%. You don't have the table to tell you for every single one. So you can't use T table for calculate this probability. You have to use Excel. So T table only tell you what is 95%. That is the only thing they tell you. So they only give you specific value. Actually, you don't have a T table. The table you have is actually inverse of T table. But let me show you. So I think this is a good question. So let me show it to you. Oh, someone say something. No one say anything. So so suppose the table we have is the T table like this. Okay. The table is give you probability. Okay. You don't have exact one, but you still have something. Okay. 99 is somewhere 190. right? So this table can only tell you the table look like this. Okay, I tell the center area was a number, right? So 3.3 is somewhere between, look at 90, right? Or look at like 100 is also fine. Doesn't really too much different, right? So look at 100. So it is between 0.01 and 0.001. I mean, actually, it's getting smaller. So what does that mean? This means the following. This table means T100, the 3.3905, negative 3.3905. The middle is 99.9%, because alpha is 99.99. Okay, so then you can calculate the tail area, right? 1 minus this number divided by 2, so it's less than 0.005, so it's so small, it's a bit 0. Okay, and the T table we will not use for this kind of properly calculated. Later you will see when we do hypothesizing, it will be more useful estimation. But for accept probability, you have to use the Excel. There's no way you can do it by hand, so don't worry. That it actually makes it easier, right? So if I ever ask you an exam, so you need to know it's just give me the Excel function, right? So that is, if I ever ask, you look at the past paper also as well. It's like if I ever ask, right? That's the thing I ask will be just how to calculate this. You just you put in, for example, this question. You just tell me, okay. That was we're asking, right? You will be just tell me, okay, this is T, this 1.698, right? 99, true, right? That you don't need to write this guy, right? This is something I'm expecting you to. I expect you to see this one, right? Of course, your assignment probably have to do it, right? But for your exam, I will not ask you to calculate. I mean, ask you give me the Excel function, right? I think that's something I asked in the past paper as well. Okay, you don't have to worry about that. I mean, if you can't do it, you have to rely on calculator. I'm not asking you. The final answer is give me this T this, right? Is that okay? Any question? Very good that you asked. Otherwise, I mean, I may forget this point. Okay. Oh, here actually I tell you how to. The next slide, okay, good question. I first forget it. This is how you do T table, because there's no T99, then you have to T90, 100. And look at 95 and 95, 1995 is this kind of table. So that's so this is between 90 and 95 is this number. Okay, it's 1.6 and 1.68. Okay, so that's why if it is within these two number, there must be between these two probability. That's the thing you can say. Okay, but this is, I think this is more advanced than you need, so just forget about it. If you really need, that's with Excel. Okay, and also this is very similar to the Z table, right? T100. Okay, so if you don't know, then actually Z table will give you a very similar answer, right? Because if you thought this is a normal, not too much different. Okay, because as I said, if you're more than 200, the sample size is very similar. Okay, but this is what we got. Okay, this because T table is like this. Okay, the T table I give you is the center area. Okay, and then you give the 2n. You'll be very clear in the next chapter when we talk about estimation. This is the table we are using. Okay, we often use this guy, often than the other case. Okay, but if you remember, when it's more about 200, right? As I mentioned, or 300 is very similar to the 1.96, right? It's very similar to the normal bell curve, right? Because 2SD should be 1.96, right? 95%. Okay. Like it's very similar to when you get more and more, it should be 1.96, right? 2SD, 95%. Because center is 95, right? Okay. Now, let me very briefly to explain a little bit of why we have a T distribution. Okay. There's a math behind, but I'm not going to talk about that. But I want to talk about this particular one. Okay. And when n is very large, okay, T is very close to standard normal. Okay, as I argue already. So that's why you don't have to worry too much when you have a large sample, right? You don't have to check the T table. Actually, going to go to normal when n is more than say 200, as I said, right? If 200, then actually you don't have to worry about T table. When T is like 60 or 70 or below 100, then probably have to worry about that. Above 100, I think normal will be fine. I mean, for most of our calculation. And I think this last slide worth some discussion. Okay. So far, we didn't say anything about how to see if the underlying is normal, right? So we assume it's normal, although it's not checkable because we can't really check the population, right? Suppose I want to know how much people to pay, what's the income. Unless I know everyone, then I can't really see. Okay. Is there any way you can try to see if normal is a good indicator, or is there any way from the data? Yes, you do. Okay. How to do it? One way is to do the box plot, right? Look at where the located data is, because bell curve, right? Must look like the bell shape, the data, right? Remember, if the underlying is bell, the data is correct, should look like bell as well, right? This is the first thing to check, right? You can draw a histogram, draw a box plot, right? The box plot tells us, is it symmetric, right? The histogram tells us whether the bell shape is it. And later we can look at the QQ plot. What's QQ plot there? I don't want to spend too much time, but the idea is the following, right? It will be sorry, I don't want to bother with that. Forget about QQ plot. That's something not very important. And you can also check two things: whether your skewness is 0 or kurtosis around 3 from the data, right? If that's the case, then it's normal. So that's why you want to learn skewness kurtosis in the first class, right? Because from data, if skewness is 0, kurtosis is 3, then it's a normal. That's a good thing, okay? If it's not normal, what can you do? Of course, you cannot do things from our class. You have to do advanced thing. You have to do, as we said, we have to do a lot of simulation exercise, do something more advanced, rely on computer, okay? And you can look in your eye to check, right? And indeed, I mean, of course, beyond the scope of our class, you can use call the JB test. The JB test is based on skewness and kurtosis, okay? And this is the formal way to show whether they're normal or not, okay? But it's way beyond the scope of our class to talk about this, okay? I'm sure undergrad will not talk about all this thing, okay? I just put it there, or you know it when you go to master level. If you want to still work on it, there's something you can check. Okay, okay, we're done. Okay, I mean, we're faster than expect, but it's good to be early, right, than late. Okay. But just review what we are doing. This class is, we know the sample mean and sample mean what it looks like, right? Sample mean, the important part is central limit theorem, look like bell curve. Okay. And unfortunately, the bell curve doesn't work very well when we don't know sigma square. So if we replace by sigma square by S, okay, and assuming the underlying is a bell curve, then we can have this idea, the T distribution, okay? But if your binary data, later you will see you don't have to worry about that, okay? When data is binary, you don't have to worry about T, okay? Because bell curve still works very well. Okay, we'll talk about that next class. Okay. Is there any question? So we will have once we're done for, so we'll quickly do some estimation part. It's not going to be something that I want to go into very deep, but I did want to talk about some estimation. I'm not going to do it very deep, but let's check out the estimation. Okay, we do it slowly, so don't worry. We are ahead ourselves, but we can't let you go because of you pay the tuition, right? And we have to be here. Okay, talk about things. Okay, so so let me talk about the structure of the rest of the class. So we know the sample mean looks like, okay, and that helps us to do estimation. We want to guess what the sample mean is. Okay, so let me get back to the idea of population and sample idea. Okay, so remember this is our world, this is a population. Okay. There are many people here. Many people here. Okay. Okay. And the question is, we can't talk to each one. Okay. And of course, the population, the thing we care about, mean, sigma square, of course, sometimes we care about the P or F, right? Something we call about the shape, right? But in this class, we are focusing on only one more way modest idea. We're focused on this guy, right? Sometimes partially some sigma square, but we are mainly focused on the mean, right? Because remember, we want to know, of course, we want to know P and F, but that's how it looks like. But it's very difficult to know. And mu is a summary of the big P and big F, if you remember, right? Because expectation, right? So you want to know that. And if you want to know that, the idea what we do is we collect data, right? We talk to, say, random pick up these people. And these people will tell us one thing. This is called sample, right? From a sample, we can calculate sample mean, sample SD. Okay? And we know from the previous topic that this guy will be a bell curve by central limit theorem, right? This one minus mu over sigma over root n. It's a bell curve, right? It's a 0, 1 bell curve. If I don't know that, I know that this is Tn minus 1, 0, like this. This guy is x bar minus mu over s over root n, right? So this is, instead I use this is the T, okay? So once I know this shape, okay, what does it earn us? Okay, you earn us the following. I know all these things, right, as well as the knowledge about expected x bar is mu as well, right? There's something, right? And the variance of x bar is sigma square over root n, right? So that is the over n, right? So the first thing to do is to say we can use this number to guess this number. Okay, from sample to population is today's topic, estimation. Okay, we want to use our knowledge from the sample to generalize to the population. Or you can imagine mu is our return of investment, right? We want to use our past stock performance to predict the future stock performance, right? We want to know the return in the past to guess what is the future, right? Because we cannot collect data from the future, right? The only thing you can do is the past, right? The population you can imagine is the future, right? Including past and future, right? And the sample is just the past, right? Because we never know the future, right? So that's the only thing is you can never know, but you can use the sample data, right? The historical data to predict what's going on in the future, right? Or we know the data, say the consumer data in Hong Kong, right? We never have business in China. Suppose we want to expand our business to mainland China. The question is how can the data from Hong Kong relate to China, right? So the idea is that you think Hong Kong and China is very similar in terms of consumer, at least for Shenzhen or Shanghai, right? In that case, we can use the information from there to have an educated guess on population, right? So estimation is educated guess using the information from sample to population. Okay, and in particular, interested in two things. One is the mu and one is sigma square. And we will show you that X bar, the sample mean is a good guess for mu. Okay, and we'll argue that S square is a good guess for sigma square. So that's two things. So we'll use this guy to estimate this. Okay. I'm sorry that we don't have time to talk about P and F because it's way beyond the scope of our class, but at least we'll try to argue that X bar is good for mu, S square is good for sigma square. Okay? Is that clear what we are saying? Okay? This will be the first part of estimation. But that's not the end. Don't worry. If that's so easy, then we're done, right? There's no need to study further, right? Because up until now, I think it's still the high school, right? But now a little bit from high school is what we call later we see interval estimate. Okay, instead of estimating one point, we estimate an interval. Okay, so what I'm saying, when we are trying to guess something, okay, so let's guess how many hours you sleep last night for the one who is sit next to you, or you got to guess me, right? And the best thing to guess will be looking at how many hours I sleep in the past few days, right? And this is you calculate that will be a sample average. That will be easiest, right? But that will not be, it will likely that you don't get it right? Because the probability that actually fall on exactly the same spot would be zero because it's a continuous random variable, right? So in order to guess, it's not guess one point, it's guess an interval, right? Interval has a probability, right? So how to form the probability, right? That is coming from, that's why you learn the bell curve, bell shape, and the T shape. And that will tell us how big is the range to guess, right? And the easiest thing you expect is I add 2SD to that. Okay. Later this is called the 2SD rule, which will become one of the things that you will be doing all the time in the class. But anyway, that will be the idea about this class is to know how to guess one point and to guess a bunch of points. Okay. The idea is like, you can imagine if I want to shoot, right? I can use a pistol to hit one point, right? That would be, if I'm good at shooting, then you're good, then you're done, right? But the point is, I usually didn't make it, right? So how can I hit the terrorists? Okay, either use the rocket launcher to bomb it, right? Or we can call for one thing, right? A bomb, right? Nuclear bomb, and bomb the whole area, right? Nothing is left over, right? So how powerful of the nuclear weapon we need, right? We have to decide, okay? So that's the idea. So now let's get back what we're doing, estimation, okay? And for estimation, we have the terminology is called population parameter, okay? The parameter is some description about the data, right? So basically, the population parameter are the things that we learned in topic 1, like population mean, population variance, population median, population kurtosis, population skewness, population IQR, whatever you learn in topic 1 is the parameter. Why I don't call it statistics? Why? Because statistics is random variable. We can't call statistics, so that's why I call population parameter. Okay, but of course, if you are not really rigorous, you're very loose, then you can call it statistics, right? You can population statistics, but it's wrong term. But if you talk to layman or outside, you can call it population statistics. It's the same thing, right? Uh, just say the mean, the variance, the mode, IQR, whatever you like, right? Something we don't know, right? Well, this is very often, right? We want to know how much people want to spend on your product, right? And how much you're willing to pay for your thing, how much time you need for wait for new customer to arrive, right? Or all the study you want to know. I mean, it's something we want to guess, right? Because this is something we're interested in, right? And here is estimator. Estimator is the way to guess based on your data. It's a rule. Okay. So you may ask, that is rule, this is the function of the random sample. How is different from statistics? No difference. Statistics is an estimator. Any estimator is statistics. Okay. But statistics need not estimate anything, right? But any estimator is a statistics. Estimator is the way you estimate something, right? You want to estimate population mean, sample mean is your estimator, right? It's the way from data to a number that you to guess the population parameter. Let me repeat what we are saying. Estimator is the type of statistics that you want to use to guess population parameter, right? Because anything can be statistics, right? Because any function, right? You can take it square, you can take a log, which need not be anything reasonable, right? But if we want to use it to, can be any use as a statistic, right? But if I wanted to guess what happened in the population, that is called estimator, right? So that's why I said no. You can see there's no different. The definition is that it's also a function of the sample, right? This definition, the first red point is called statistics, right? So estimator is a statistics to estimate parameter, right? Because statistics can be used for anything, right? But statistics with purpose, with something, with the purpose of guessing, is called estimator. Okay, so that's nothing new, but we know sample mean is an estimator, sample variance is also estimator. Okay, and very often it depends on n, so we are going to be a little bit tricky on the, I mean, picky on the right term is if you want to guess theta, okay, we will write theta n hat. Okay, yeah, very often write this way. Okay. So sample means sometimes we write this way, right? But in some textbook they will write mu hat. Okay. And sample variance, sometimes we write S square. Okay. But some textbook will write sigma hat square. Okay. Because they are to guess sigma square. And this is to guess mu. Right? So that's the idea. Is that okay? So estimator is a statistics to guess some parameter of interest. Now, a technical point, I don't think it makes sense, it make a difference, but this is very important. We distinguish estimate and estimator. Estimator is a random variable. An estimate is a number. Once you collect the data, you calculate through estimator, you get an estimate. Estimate is a number. Okay. Once you collect the sample, you collect the observation, you have the number, and the number you follow the estimator, you get estimate. Okay. It's a number. And at the beginning, I mentioned that there are two types of estimators. One is point estimate. Okay. Point estimate is this. I told you already. Point estimate is this. Ooh, it's a pistol, right? And what's interval estimator? So you're going to hit the target, dong, the point. Okay? And what is interval estimator? Interval estimator is like this. This is a rocket launcher. Okay, when you hit it, it just explodes this whole area, right? Or you don't like this, this is this. Okay, it's going to bump, or the N word, the M bomb or A bomb, right? M bomb or A bomb, right? N bomb, right? Or some people like H bomb, right? Hydrogen bomb, atomic bomb, or nuclear bomb. You bomb the whole area. Okay. So what is point estimator? Okay. This often we say, right? What in the news in everyday morning, right? You would the financial news before the market open, right? You ask an expert comes in and talk, what is the guess of Hang Seng Index today, right? And the guy will say, okay, this today I guess it will be 28,000, right? And that is point estimator, right? If they tell you exact number, 28,000, right? If they tell you, okay, today I guess number 20,000, the point estimator, right? And if they say, okay, no, it will be 27,000 to 29,000, okay, give you range, it's called interval estimator, right? Right? So that is the idea, right? So it's giving a interval, not giving a precise answer, right? So probably someone will ask, right? When a boy meet a girl, right? And the girl asks the boy, how many girlfriends do you have, right? And the boy said, the boy don't want to say anything, right? Maybe two, right? Maybe 10, right? Maybe 10, maybe say 10, right? Maybe 5 or whatever. Give a number. Then it's a point reply, right? But you say, okay, how many girlfriends do I have? Okay, maybe 1 to 10, right? Don't give you anything, right? Maybe 0 to 10, right? Right? Then well, you don't, then it's interval, right? So that you don't give a precise answer, it's interval, right? Point is like you give a precise answer, right? So that would be the idea. Okay. And for the point, you know very well, actually similar to what we learned in the chapter 1. And you don't really learn too much from that, but interval is the thing that will require you to understand the bell curve. To This is what different from high school, right? High school, you may have learned already this one. There's something that you may not learn this interval. It's something that you would able to give. Why give this range? Must be some reason. We will do it next class, but this would be the point. Okay, we'll talk about point estimate first, and then we'll talk about interval. Okay. And before we end, I want to. Okay, so I already said, right? The TV interview, right? If you give one target price, it's point estimate. If you give you a range, upper bound, lower bound, it's interval. Point estimate. Okay. And turn out that, there are many ways to estimate one thing, right? Then there will be actually 3 criteria many criteria, but these 3 are accepted to be good one. First, unbiased. Second, efficient. The first, consistency. Okay. I can talk about unbiased, and that would be the end of today. Okay. Unbiased means already I mentioned about the football, right? Cristiano Ronaldo and me are unbiased football kicker. Why? Because Messi or many stars, they kick the football, they can always kick in, right? Very good, right? For me, right, which is me is here, okay, me, okay. What I'm going to do is I'm very bad at football, okay. I don't hit inside, but I hit outside, okay. I don't get in the ball, I don't get the net, but on average, I'm in, right? So on average, I'm getting in, but I'm not getting in every time. I'm very far away, right? Sometime here, never get in. It's also okay. But on average, it's in, okay? So on average is exactly what we want to get, then yes, okay? Suppose I want to shoot some people, right? Suppose I want to say this guy, right? He's a bad guy, okay? Then if I don't know who is good at shooting, right? Maybe bad, or maybe, I don't know. A good policeman would every time shoot the bad guy, right? And kill the guy, okay? But me, again, it's me here. Me, right? I have a maybe James Bond, right? James Bond. James Bond is very good, right? James Bond, right? Me, right? I'm going to shoot the guy. I'm not going to hit anything, but I hit around him, right? But on average, hitting the target, right? That's like a lot of I don't know. Have you seen any magic show, right? Some guy throw a knife, right? You don't hit the guy, but on that, right? Hit around him, right? But on average, it's hitting the target, right? But that is called unbiased, okay? Or if you like the arrow story, something like this. So you want to hit them, right? If you hit it all the time, it's unbiased. If on average is inside, it's also unbiased. Okay, it's just very minimum requirement. It doesn't require you every time you hit it. Even if you don't hit it, if on average hit it, then you're done. Okay, we'll talk about unbiasedness next class as well. But I will say one last term is, as we said, is X bar is mu. And the next thing is S square is sigma square. So this justify overall we want to look at n minus 1, not n. Okay, that's why you can't use divided by n. You know n is wrong. You have to divide by s n minus 1. So that's it. Okay, I answered the question we posed at the very beginning of our course. Okay, we'll do it more in the next class. Have a nice weekend. Hope you're not so tired next time. Yeah, you can go. It's done. I'll see you next week. I'll answer the question you might have.